Hello to everyone from around the world, and welcome to today's webinar, What on Earth is Jitter Amplification and Why Should I Care? This is part 3 of the series titled Overcome High-Speed Digital Design Challenges, brought to you by Agilent Technologies and DesignCon Community. We have just a few short announcements before we begin. This webinar is designed to be interactive, so please ask questions at any time during the presentation by typing in the text area and clicking the Submit button. Our presenter will answer your questions at the end of the webinar, but please enter them whenever they come to mind. Later in the program, we will ask you to complete a short survey. Please take a moment to fill this out. Your feedback is important to us and will provide Agilent Technologies and DesignCon Community with valuable information on the subjects covered in this webinar and how we can improve future broadcasts. The survey will open for you at the beginning of the Q&A session, and additionally, you can launch the feedback form using the survey button. And now on to the presentation. It's my pleasure to introduce our presenter, Fengyi Rao, Master R&D Engineer at Agilent ESOF EDA, and joining us during the Q&A is Colin Warwick, High-Speed Digital Product Manager for Agilent ESOF EDA. Welcome, Fengyi and Colin. I'll now hand it over to Fengyi to begin the presentation.
Okay, thank you. Welcome, everyone. In this presentation, I'm going to discuss the jitter amplification. Here is the agenda of this presentation. First, I will explain what jitter amplification is, and then I will demonstrate the mechanism of amplification in using the clock channel as an example. And then I will show the impact of the effect on channel analysis. So what is jitter amplification? Let's take a look at the random jitter example. Here we have a channel, and on the left is the input signal. It's a perfect square signal that represents the bit strings in the input stimulus. And in these square waves, the transitions from between 1 and 0 are modulated by the random jitter. And on the right of the channel is the output signal, and you can see the signal is being low pass by the channel loss compared to the signal on the left. And again, the output signal has a certain amount of jitter due to two factors. One is the intersymbol interference that is introduced by the channel dispersion. And the second type of jitter in the output signal is the random jitter induced by the random jitter in the input. Okay, and because the ISI and RJ are uncorrelated, therefore they are RMS. The RMS of total jitter is the sum of ISI RMS square and the RJ RMS square, as you can see in the formula on the right side of this slide. Okay, and ISI RMS can be measured by turning off the input jitter and then measure the output signal RMS. And the random jitter at the output is induced by the input RJ, and when the jitter is small, the output RJ is proportional to the input RJ. And when the ratio between the RJ RMS of output and input are bigger than 1, that is when jitter amplification happens. So we can see the effect of amplification has nothing to do with ISI. It's purely happen between the induced RJ that introduced by the input jitter. Okay. Similar amplification effect can occur to other type of jitter, In the DCD case, amplification means the output peak-to-peak DCD is bigger than the input peak-to-peak DCD. For the SJ case, sinusoidal jitter, amplification means the output SJ amplitude is bigger than the input SJ amplitude. Okay. The effect can happen in a perfectly linear, passive, and noiseless channel. As we will see later in this presentation, the effect is caused by channel loss. Specifically, it arises from a lower attenuation at the jitter lower sideband than at the signal carrier, which is at a higher frequency compared to the jitter lower sideband, as you can see in this plot. So we will get into the detail of the mechanism in the next section of the presentation. Now let's review some measurement and simulation results of the effect. The effect was first reported by Intel in 2006 on DCD and RJ in a clock channel. In the paper, the authors studied two 15-inch passive clock channel at 6.4 and 9.6 gigabit per second data rates. One channel has a 100 ohm matched backplane. The other one has a 81 ohm mismatch backplane. I want to point out that the benefit of studying clock channel is that the ISI is 0 due to the periodic 1010 clock pattern. Therefore, output jitter is entirely induced by the input jitter. Also, the amplification can be measured directly from the output jitter without having to subtract the ISI. And here is the result that presented in the Intel study. They studied two effects, the DCD and RJ. For DCD, the amplification is measured by comparing the peak-to-peak DCD between the output and the input. And for RJ, the effect is measured by comparing the RJ RMS between output and input. Okay. And at bottom, you can see the measure and simulation results for DCD and RJ. We noticed that both amplification increase with data rate. In 2007, Rambus did similar study on DCD and RJ, again in clock channel. On the top, I show the result for a 24-inch PCB channel at data rate up to 12 gig. The figure shows DCD and RJ amplifications versus channel loss. The solid line are the simulation result, and the dotted lines are measure results. It's similar to the Intel results. Both amplifications increase with the signal loss. Interestingly, in this paper, the amplification results in 3 different channels with a 16 and 24-inch PCB clock channels, each at different data rates between 2 and 6 gig, are plotted against the signal loss. Okay, and this result shows that the DCD and RJ amplification scales uniquely with channel loss, and this strongly indicates a link between amplification and channel dispersion. In 2010, DesignCon actually report RJ amplification in data channel. What the author did is they simulate a passive data channel at 1, 3, and 5 gig data rates with PRBS 31 patterns, and each in the simulation, a million bit was run through the channel. And first, the input jitter is turned off, and then 1 million bit was simulated, and the jitter is measured at the channel output. That gives us the ISI jitter. And then the input RJ is turned on, and then the simulation was repeated, and the jitter RMS is measured again at the channel output. That gives the total jitter RMS. So, and with the total jitter and the ISI jitter, the output random jitter RMS can be extracted, and then the result is compared with the input RJ that is injected into the input signal, and that will give the RJ amplification factor. And as we can see, similar to the clock channel, the RJ amplification increase with data rate. In 2012, Agilent and Juniper report results on SJ, DCD, and RJ in clock channels. 4 passive channels with different loss are simulated with 1 million bit, and each channel is investigated under different data rate up to 16 gig. Okay. And it was found that as shown on the left figure, the SJ amplification, which is the ratio of SJ amplitude between output and input SJs, increases exponentially with SJ frequency. Okay, and similar to the Rambus result, DCD and RJ amplification are found scale uniquely with channel loss. Okay. Now we have seen the amplification is demonstrated in various study and in different type of channels. Now, how does that happen? It's quite counterintuitive to think of a linear passive noiseless channel can amplify jitter. So in the next section, I'm going to demonstrate the mechanism of the effect by analyzing jitter propagation in clock channel. As I mentioned earlier, the benefit of studying clock channel is that the ISI is eliminated by the periodicity of the 1010 clock pattern. Therefore, output jitter is entirely induced by the input jitter. Furthermore, if the channel is lossy, high order harmonics in the clock signals are heavily attenuated and can be ignored. Therefore, the clock signal can be approximated by a sinusoidal wave, and the jitter in the signal can be represented by the phase modulation in the sine wave, as we can see in this figure and formula here. Here, omega 0 is the fundamental frequency of the clock signal, or half of the clock data rate, and phi is the phase modulation that represents jitter. Now let's consider a SJ in the input signal at and assume the SJ frequency is at omega. So SJ will have positive and negative branches, and once you put that phase modulation, sinusoidal phase modulation into the sine wave signal, we immediately get the 3 branches in the frequency domain. First is the carrier at omega 0. Second is the upper sideband at omega 0 plus omega due to the positive branch of SJ. And the third component is the lower sideband at omega 0 minus omega due to the negative branch of Sj. Okay. After this signal pass through the channel, these three components will multiply with the transfer function h at three different frequencies. Okay. Now, it's interesting to see that in a typical lossy channel, the transfer function decays exponentially with frequency. Therefore, the lower sideband will experience less attenuation than what the fundamental frequency will experience. The magnitude of lower sideband at the output signal will actually have a gain factor compared to the carrier magnitude. And since the phase modulation is determined by the ratio between lower sideband and the carrier, therefore the difference of attenuation between lower sideband and the carrier actually introduce a gain factor to the phase modulation at the output signal. And that again leads to the jitter amplification. And that is the mechanism of amplification in a lossy channel. Now, if we work out the math, we'll see the output signal can be written in, expressed as the equation at the top of this slide. You can see, in addition to phase modulation, the output signal also has a amplitude modulation that is caused by the input Sj. And so the output signal has impairments in both timing and voltage. Okay. The output signal Sj is determined by the phase modulation term, which you can see is also a sinusoidal at frequency omega, but with a different amplitude. Therefore, we can calculate the Sj transfer function or the amplification factor by comparing output Sj amplitude and the input Sj amplitude. And the amplification factor of Sj is given by the equation at the bottom of this slide. As we discussed earlier, the effect of amplification is dominated by the lower sideband, and amplification is the result of a smaller loss in lower sideband than in the fundamental. I also want to point out that if the reflection in the channel is small, we can replace the transfer function h with forward S parameters. We can apply the same theory to DCD. DCD is just a special case for Sj at the jitter frequency omega equal to the fundamental omega 0. Therefore, we can use the previous formula to get the DCD amplification factor, which is shown in the middle of this slide. We notice that for DCD, the lower sideband becomes a DC shift. Okay? And the channel output signal becomes a DCD plus a fundamental plus higher order harmonics, which can be ignored under channel loss. Therefore, the output signal has a sinusoidal at fundamental, but is shifted vertically by the DC shift. Now notice DC shift is proportional to the transfer function at 0 frequency, which is always around 0 dB regardless of the channel loss. The fundamental, however, is proportional to the transfer function at omega 0. And so you can see if the channel loss is the bigger the channel loss, the smaller the fundamental amplitude, therefore the larger the DCD effect. For random jitter, we assume input RJ is a white noise with flat power spectral density. Therefore, the output RJ power is given by the integral of the SJ transfer function up to the jitter Nyquist frequency, which is the omega 0. And then we arrive at the RJ amplification factor given by the bottom of this slide. And the RJ amplification factor is defined as the RJ RMS ratio between output and input. So far we have worked within the framework of sinusoidal representation. The real signal is actually more like a square wave, at least at the input. So how does the effect look like when we use a square wave representation? So in square wave, we can model the 1010 signal with this square wave, and the transition of the square wave between 0 and 1 are modulated by the input signal. And assuming the channel is linear, we can calculate the output signal by the linear superposition of step responses, as we show in the middle of this slide, where R is the step response and T is the UI, unit interval, and tau in is the input jitter. Notice that when input jitter is 0, there's no ISI in the output. The output signal 0 crossing are uniformly spaced by exactly 1 UI. Okay. When the input jitter is turned on, the output jitter can be measured from the crossing time shift. Okay, and that is given by the equation, the second equation in this slide. Here, the small h is the derivative of the step response, which is the impulse response of the channel. Okay, you notice the alternating sign minus 1 to the nth power is actually the result of the 1010 clock pattern. Okay, and TD is the nominal channel delayed. Okay. Now, if we consider a sinusoidal jitter, the output jitter can be rewritten in the form of the transfer function, where the capital H is the Fourier transform of the impulse response. And we notice the output jitter is again a sinusoidal with a different amplitude. Therefore, we can obtain the SJ amplification factor within the square wave formulation, which is given by the first formula. Now, if we assume the higher order harmonics can be ignored and we leave only the fundamental harmonics, we found that the square wave formulation is exactly the same as the sinusoidal results we obtained earlier. Therefore, we found that the two representations, namely sine wave and square wave, the results converge after we ignore the high order harmonics. Well, this is as expected. Now we're going to look at the scaling of DCD and RJ. To do this, we first use a loss model, which is has a exponential decay of the transfer function with frequency. This is a typical behavior of lossy channel. And if we plug that into our SJ formula, we have the SJ amplification factor. We can see that this factor is always bigger than 1 for any SJ frequency, and also the factor grows exponentially with SJ frequency. We can use the loss model in DCD and RJ and to get the factors shown in the middle of this slide. And again, the DCD and RJ amplification grows exponentially with data rate. We can go one step further to rewrite the DCD and RJ formula in terms of channel loss at the fundamental frequency, and that gives us the scaling of amplification versus the loss measured at omega 0, as shown at the bottom of this slide. So now we have a theory of amplification, and how does that compare with simulation? To verify the theory, we simulate 4 clock channels at different losses. The input clock signal is represented by square waves, as we described earlier, with jitter applied at the transitions. And the output signal is computed with step response superpositions. Okay. And for each simulation, we run 1 million bits. Okay. So here is the result for RJ. First, we show the eye diagram of channel 2 at 10 gigabit per second with a input SJ at amplitude of 5 picosecond and frequencies at 0.5 and 2 and 3 gigahertz. We can see as the SJ frequency increase, the output SJ amplitude become larger. We also notice a amplitude modulation or amplitude noise at the output signal that induced by the input SJ, as predicted by the theory we discussed previously. Okay. And at the bottom plot, we show the output SJ distribution function for different SJ frequencies. We can see at 0.5 gig, the output SJ amplitude is 5 picosecond, same as the input SJ. But as the SJ frequency become bigger, the output SJ amplitude is bigger than the input SJ, and that clearly shows the amplification result. Here we plot the SJ in channel 1 at 10 gig data rate, and in channel 2 at 10 and 20 gig data rates. Okay. We also compare the simulation result with 2 theoretical predictions. In the first theoretical result, we use the formula based on the S parameter, S21. And in the second theoretical result, we use the loss model formula. And we can see that the simulation results are in excellent agreement with both theoretical predictions. And the loss model turns out to be a fairly good approximation in these channels. Again, we see the SJ amplification grows exponentially with SJ frequency. Also look at the results of channel 2 at 10 gig and 20 gig data rates. We notice the amplification is actually insensitive to the data rate. Is only depends on the SJ frequency, and this is predicted by the loss model. Here is the result for DCD in channel 1 and 2 at different data rate. And again, we use 2 formulas to calculate the theoretical values, and these values agree with the simulation results pretty well. for RJ, on the top we show the output RJ distribution in channel 1 at different data rates. The input RJ RMS is 1 picosecond. You can see as the data rate increases, the RJ RMS also grows. And at the bottom, I show the RJ amplification factor in channel 1 and 2 at different data rate. And again, the simulation result and theoretical results are in good agreements. And RJ is found to grow exponentially with data rate. In this slide, I show the DCD and RJ amplification scaling with channel loss. So the results of all 4 channels, each at different data rate up to 16 gig, are plot against the insertion loss measured at the fundamental frequency. We can see the amplification scale uniquely with channel loss, and the theory matches the simulation results very well. So now we have seen why the amplification is happening in a lossy channel, and what does that mean when we analyze the channel link and performance. So the implication of the effect is that when we model Tx jitter when simulating a channel's performance, we must apply the Tx jitter in the input signal. So therefore, the input jitter can experience the channel loss. And this is true for both time domain or bit-by-bit simulation and for statistical simulations. Here is a physical model of Tx jitter. For each pulse, the rise and fall edges happens at the near the ideal rise-fall edges, but with a certain amount of jitter applied to the transitions. Okay, and in the jitter, there are 3 different components. First is the random jitter. Second is the sinusoidal jitter, and third is the duty cycle distortion. In many link simulation tools, it is popular to add Tx jitter in the post-processing step by convolving Tx jitter PDF with the ISI PDF. And this is the approach that is taken in a popular StatI approach. And now, as we learn from this presentation, this approach is fundamentally incorrect because it misses jitter amplification. Therefore, it underestimates the jitter at the channel output. Here I show an example of TXRJ. In the plot, the blue lines shows the BR from a bit-by-bit simulation running a million bit with a PRBS31 pattern. And the red curve shows a statistical simulation with the Tx jitter. In both the red curve and the blue curve, the Tx jitter is applied into in the input signal. Therefore, the jitter amplification is captured in the result. We can see the red line and blue line agrees down to the statistically significant level around 10 to minus 5, and the blue line dropped vertically beyond that point because there's simply it cannot they resolve any smaller probability beyond that point with 1 million bit samples. As a comparison, the pink curve is the result of using the post-processing approach to add Tx jitter directly to the ISI result. As we predicted previously, the post-processing approach underestimate the output jitter. So in summary, we have learned that jitter is amplified by channel loss, and this can occur even the channel is linear, passive, and noiseless. We also show that amplification arises from smaller attenuation in jitter lower sideband than in the fundamental. In lossy clock channel, jitter is amplified at any jitter frequency below the Nyquist, and the effect grows exponentially with jitter frequency and data rate. We found that DCD and RJ amplification scale uniquely with loss in clock channel, and when simulating a linear performance, it is critical to apply Tx jitter in the input signal in order to capture the amplification effect. Okay. And here are some reference you can find that is used in this presentation. And thank you for your time. And with that, I will pass it to Colin.
Thank you, Fang Yi. So let's do some Q&A. And the first question is from Saeed. It says, how does one apply input jitter in ADS IBS-AMI simulations? In IBS-AMI is the same. Use in ADS we use the same jitter model as we show in this slide here. Let me show it in the screen. So this is the jitter model we use for Tx component. In IBS-AMI simulation, the jitter is handled by the simulator. So we in ADS apply the physical model of Tx jitter into the stimulus signal, and that signal is passed into the Tx AMI and then go through the channel. Very good. A couple of questions about acronyms. You might want to expand some of the acronyms for people who aren't familiar with them. SJ, DCD. Could you just quickly explain those acronyms?
Yeah. SJ means sinusoidal jitter. DCD means duty cycle distortion.
Very good. Next question is also from Saeed. He said, should the jitter depend also on return loss? Does jitter amplification depend on return loss?
In general, yes. So the way that jitter amplification depends on return loss is actually included in the channel transfer function. Let me show the yeah. So you can see the amplification factor is a function of the channel transfer function H. Okay, and H is determined by both the insertion loss and return loss.
Yeah, in general, it's all four parameters. Good. Next question is from Jim, and he had a question about slide 11. He wanted to know, is phase modulation as mentioned on slide 11
is it the same as phase distortion? Are those two terms synonymous, or are they different?
I'm not sure what the definition of phase distortion means.
Okay. Or maybe we can take one offline, then we'll get a clarification unless Jim wants to post a clarification of that one. Okay. Are all these, this is from Dave, are all these jitter amplification effects included in ADS simulation models?
Yes.
Specifically, 2009 was the first release that has channel simulator, right? That's where you'd look for these types of modeling these effects, correct, Bang-Yi?
That's right. Yeah, and in particular, the effect is included in both bit-by-bit mode and statistical mode.
Good. Excellent.
Yeah.
And it works for both the built-in models and the IBIS AMI models also, is it? Correct?
That's correct, yeah.
Good. Okay. Next question. This is kind of a long question from John Bay. In the case of HDMI or DDR, clock signal is transmitted along with the data signal. That is, both clock and data suffer jitter amplification. This is kind of a sort of synchronous clocking. When data is fetched by the clock, what will be the impact of jitter amplification? And can ADS simulate the statistical eye with reference to a non-ideal clock? I think the last part is answers no, right? We assume a embedded clock in channel simulation so far.
In principle, the synchronous clock can be simulated. Actually, in the IBIS AMI approach, this effect can be taken into account because the RX AMI model could return its clock times, and that is used by ADS to center the eye in the data signal. Okay. In terms of how the clock jitter and data jitter interact with each other, there's no general answer to that. It all depends on how the jitter synchronize between these two, between the data signal and the clock signals. So in some case, they can actually cancel. Okay.
Yeah, that sounds really cool. Good. Okay, next question is from Drew. I'm not sure I understand the premise of this question, but I'll read it out as Drew's written it. Why do you assume ISI is unbounded, i.e., why is RMS a valid measure of ISI? I'm not sure I understand that, because RMS can be applied to both bounded and unbounded.
Yes. I think that is probably have to do with this slide.
Okay.
Well, this slide, this equation here doesn't mean ISI is bounded. Okay. This relation holds for any random variable, regardless whether it's bounded or unbounded, as long as ISI and RJ are uncorrelated.
Right. So RMS doesn't imply bounded or unbounded. It could apply to either type.
That's correct. Yeah.
Okay, we have a clarification from Jim about the phase distortion question. He's saying phase distortion is the slope of phase versus frequency. In other words, different frequencies can take the same amount of time to go through the channel. And that was related to the earlier question about is phase distortion the same as phase modulation?
Okay.
Does that help?
Okay. Yeah, I think then in that context, phase distortion means actually the phase velocity dispersion in a lossy channel, meaning different frequency has different phase velocity because of channel loss or channel dispersion. So in that sense, phase distortion is not phase modulation, because in our analysis, the input signal that comes even before the channel already have a certain amount of phase modulation, which represents the input jitter.
Okay. So a question here from Harry. From the other direction, if I over-equalize the channel loss, can you attenuate the jitter?
In theory, it's possible. Yeah.
Wouldn't the upper sideband get boosted though? I'm not sure.
Yeah.
You have to be careful just to boost the carrier, not the sideband, right?
Yeah.
Either slope could kill you if you. I guess in principle you could do.
Yeah. So you have to design your equalizer carefully. Yeah.
Yeah, it would have to just boost the carrier, not the sideband. Okay, next question is from Bo. Jitter amplification is dependent on the channel loss and the data rate. If the data rate is fixed, what are the options to reduce jitter amplification?
Yeah, so the option is to equalize the channel loss.
Yeah, either make the channel very flat,
yeah,
or equalize it, higher quality channel. Yeah.
As you can see here, if you make the transfer function of H a flat over a certain amount, over a certain range of frequency, this jitter transfer function is actually equal to 0. I mean, actually equal to 1, so there's no amplification. That's actually how the equalizers work. Yeah.
Yeah. Okay, next question is from Inho. Is asking, how do you handle the impact of jitter if channel crosstalk exists? Can we handle that case?
Yes, we can handle that in ADS. So in ADS, we actually can assume two types of crosstalk. One is the crosstalk is synchronous with the victim channel. In that case, the crosstalk signal is considered is being added to the victim signal, and from there we can calculate the crosstalk effect. In asynchronous crosstalk, the phase is drift between the victim and the aggressor, and with that we average the crosstalk signal over one UI of the crosstalk signal, and then we add that effect into the victim signal, assuming that these two are uncorrelated, and the crosstalk is an additive signal. So the exact approach actually is described by in one of the reference given in this slide. You can find the description of crosstalk effect in reference 3.
Good. Next question is from Daniel. Does ADS have a means, this looks like it's related to bird 123, does ADS have a means for margining the jitter like the J-bird to seek the edges of the performance of the receiver, like a jitter stress test?
Have mean to, I don't quite understand the question.
I think it's about the, do we have a GUI for the jitter stress test like we have, we added in ADS 2012, that bird 123.
Okay. Yeah. In I think in the ADS 2012 release, we allow user to inject jitter into the system from the ADS UI.
Yeah, we call it jitter stress test. It was part of the bird 123 enhancements, right?
Yes. Yeah.
Good. I think that one off. Next question is also from Inho. What is the most effective equalization methodology at the receiver to cancel or mitigate jitter impact? Is it a continuous time linear equalizer or a decision feedback equalizer? Any thoughts on mitigation?
Depending on what the data rate you're talking about. At high data rate above 10 gig, you have to use a combination of both. The reason is that the CTLE will cancel a majority part of the channel loss, but it will still have some remaining jitter, and that will be taken care of by the decision feedback equalizer. So typically in data rate above 10 gig, you have to use both. Yeah.
Okay, good. The next question is from Bo. He says, is there measurement jitter data that correlates the theory and simulation results with measured data? Do we have any measured data?
We do not have measured data ourselves because we are software. We develop software, but there is some data that show in the Rambus paper. Let me go back to that slide. So here is the Rambus result reported in 2007. You can see they did the simulation, which is shown in the solid line, and the measurement we show in the dotted line. Yeah.
Good.
And by the way, they measure the jitter in clock channel by using a Agilent oscilloscope.
Yeah. Good. Next question is from Dave. Why doesn't equalization remove the jitter amplification caused by lossy channels, or maybe does equalization remove?
It does,
yeah. So it
yeah.
does. So yes, it can be done, but you have to equalize carefully.
Yeah. So in the formula, the transfer function H includes equalization effect if the equalizer exists in the system.
Yeah.
Yeah.
Okay. We've probably got time for about 2 more questions. There's quite a few of these we haven't gotten through. If we haven't answered your question, we'll do it by email because there's about a dozen questions left and I can't get through them all. I'll just take 2 more. One of the slides you mentioned that jitter amplification is insensitive to data rate. Can you explain why that was? In most cases, jitter amplification was very sensitive to data rate. Is there a slide?
That is, that is only for the SJ case. Let me, yes. Yeah, so that has to do with the lossy model, the exponentially lossy model, which is a very good approximation in most of the channels. With that, you can see actually the amplification factor. In the amplification factor, the omega 0 term is cancelled out, and then what's left is only the SJ frequency. Okay. But that is only true for SJ, and in DCD and RJ, there's solely determined by the data rate.
Good. We'll take a couple more. One's a quick one from Kai. What simulation tool did you use?
ADS.
Yes. And Youssef says, does this analysis apply for high frequency range only? How does it play in low frequencies? That kind of hockey stick knee, I suppose, is the question. Why is it?
I'm not sure what high frequency means. Does that mean high frequency jitter or high frequency signal?
I assume it meant the data rate, but I could be wrong.
Well, as a matter of fact, this analysis applies to both high frequency and low frequency, because you can see there's nowhere we assume where the frequency is high or low.
So the reason it takes off at high frequency is because that's where the loss kicks in. Is it? It just depends on the loss versus frequency. Is that?
That's true. Yeah.
Yeah. So it's really the shape of the curve versus the frequency you're working at. Yeah. Very good then. I think that's we're at the top of the hour. We'll follow up with. I'm sorry to disappoint people who didn't get their questions answered, but we'll follow up by email. And can you push the wrap-up slide for me, Fangy, or can I do that myself, I think?
Sure. Yeah.
I think I can do that. So next steps, please visit our website to look at the products that Fangy is demonstrating here. This is the URL. I also have a blog. You can read interesting tips and tricks about signal integrity at that blog. Email. And this webcast is part of a series of 3. This is the third one on 3 different topics. If you want to look at the on-demand versions of the other 2 webcasts that we held in February and March, go to this URL and you can see the other ones, which are about memory channel design and modeling optical fibers. There's various other webcasts there as well. Okay, Jessica, do you want to take us home?
Sure. Thank you very much, Colin, and thank you for a great presentation and Q&A session. I would like to thank everyone for attending today's webinar, What on Earth is Jitter Amplification and Why Should I Care? Brought to you by Agilent Technologies and DesignCon Community. Please fill out and submit the survey at this time if you haven't done so already. By completing this survey, you'll provide Agilent Technologies and DesignCon Community with valuable feedback on the subjects covered in this webinar and how we can improve future broadcasts. This presentation will be available shortly in an on-demand format, and as a registered user, you will receive an email with detailed information on how you can access the on-demand replay of the webinar. The on-demand will also include a PDF copy of the slides used in today's discussion. This webinar is copyright 2013 by DesignCon Community. The presentation materials are owned by or copyright by Agilent Technologies, which is solely responsible for their content. The individual speakers are solely responsible for their content and opinions. We hope you will join us for future webinars. For a current schedule of live and on-demand events, please visit us at designconcommunity.com. Thank you very much for joining us, and have a great day.